Wake up. Okay, now we talk about the electrical system. We have seen the mechanical system, three different types of mechanical system like linear motion, rotational motion, and some linkage systems of the mechanical parts. Now we talk about the electrical system. What are the electrical system? Electrical circuits. Electrical circuits are having two different types of components. In electrical system, there are two types of components: active components, we call it active elements in electrical system. Active elements, and there is another one we call it passive elements. So active elements are voltage, current. These are the active elements. Passive elements we call it R, L, C. What are R and C? What is V, I? Anyone? What is V and I? V, voltage, I, current, R, resistor, L, inductor, C, capacitor. R, L, C, resistor, inductor, capacitor. These are passive elements, and voltage and current are the active elements in an electrical system. So these are the basic elements of the electrical system. And so what is this? Resistor, R. This is R. So I will just write it here. This is V, and the current flow will be I, and resistor R. This is inductor L, and this is capacitor C. R, L, C. These are the basic elements. Now you already know about the Ohm's law, right? Ohm's law, you already studied that Ohm's law in your school. You studied that. What is the Ohm's law? Ohm's law is that the current flow is directly proportional to, if there is a current flow I, and the current flow will be directly proportional to the voltage of a conductor to the voltage directly. So this one we define it, V is proportional to I. The current flow is directly proportional to the voltage applied to a conductor. Voltage applied to a conductor. V is proportional I. So we write it in this way: V equal to IR. So where R is the resistance. Ohm's law we already know. So what is actually it is in time domain. So we can write it is in Vt is equal to It into R. It is in time domain. So if you are converting this in Laplace domain, Laplace transform. Do the Laplace transform. You already know, I already told you about the Laplace transform. What is the Laplace transform? If you want to convert this, suppose Laplace transform of xt is equal to xs. Laplace transform of xt will be equal to xs. We do the Laplace transform to convert from time domain to the frequency domain. We have seen that in our previous lecture. So this one we write Vs equal to Is into R. Vs equal to Is into R. In here, it is mentioned VRS equal to IRSR. Why? Because this is for the resistance. That's why it is used R. If it is for the inductance or inductor or capacitor, it would be L or C. So to differentiate voltage of resistor from inductor and capacitor, it is used R. So you can use, because it is happening for resistance, you can use this. VRS equal to IRSR. This is just a subscript. So this is the Laplace transform. Now that is for the DC circuit. Do you know about the DC and AC? DC and AC. What is DC? This is DC. What is an AC? Alternating current. Direct current. Alternating current. So what is the direct current? Direct current like this. And alternating current is this sinusoidal current. Which current it is here? AC, no DC. Your phone. In here, no, in your phone. In the DC, it is DC, right? It is DC because there is a battery. Battery is DC. Battery is DC, and here it is the AC current. It is AC current, and this is DC current. We define it in this symbol. This one we define it in this symbol. If you see this is AC. If you see this is DC. Now Ohm's law. This is for the Ohm's law for the DC system. Now what about the Ohm's law for the AC system? In AC, it is different. Why? Because in an AC, there is two more components are involved. Two more components, L and C. In AC, there is two more components are involved, inductor and capacitor. In DC, there is no inductor and capacitor, no inductors and capacitors. But in AC, there will be an inductor and capacitor. So, this is R, L, C, three components are involved. So because now there are three components are involved, we call these two, we call it reactance. R, what is R? Resistance. The opposite of the current flow, opposition of the current flow. R is the opposition of the current flow. So reactance is also the same. The opposition of the current flow due to L and C, inductor and capacitor. So together we call it reactance. Reactance we define it X. We define it X. So here for the AC system, this is for AC system. If in this way here in this direction, if we draw R, in this direction we draw X, R and X, because now we don't have, we have R plus Jx. So R plus Jx, we can define it. This is R. This is Jx. This imaginary. This is real plane. This is imaginary plane. So R and Jx. So if you just write, and this, if you add the third one, the corresponding one we call Z, impedance. Impedance. Together we call it impedance. So Z will be equal to R plus Jx. Z is the impedance. Impedance is the opposition of the current flow in the AC circuit. AC circuit. Resistance is the opposition of the current flow for the DC circuit. Z, impedance is the opposition of the current flow for AC circuit. This is for the AC circuit. So we can find out this Z is equal to root over R square plus X square. And also we can find out the theta. Theta is equal to tan inverse X by R. That is how we can find out the magnitude of phase. Now what is X? What is X? X is XL minus XC. X is the reactance. Reactance opposite the current flow due to inductor and capacitor. And due to inductor and capacitor, there are inductance and capacitance. XL is the inductance, XC is the capacitance. So XL, we call it inductance. And XC is the capacitance. That's the whole basics of the AC system. Basics of the AC system. So slope for the DC we just use V equal to IR, but for the AC system it is a bit complicated because L and C are involved, and together L and C we call it reactance. And that reactance will be added and it will be added on the imaginary axis Jx, and we can find out magnitude and phase by using these two equations. And now the X is the combination, is the difference of inductance and capacitance. So Xt will be equal to XL minus Xc. So now we will talk about the mathematical modeling for capacitor and inductor, because we already have seen the modeling for the resistor. This is the modeling equation for the resistor. So what about the capacitor? Capacitor. So if this is the C, so the voltage, where it is the relation of the voltage and current. So because we are talking about the capacitor voltage, we are using C for the capacitor. VR is for the resistor. So VC is equal to integration of I dt. So we are talking about the capacitor current, so we will use C. Now it is in time domain, so we can write it VCT in time domain. Integration of IC t dt. So here there is a capacitance. So it is 1 by C. So the whole equation is 1 by C integration of I dt. The capacitor voltage is equal to 1 by C, where C is the capacitance, and Integration of ICDT. Now, if we use the Laplace transform here, Laplace, so how do you get the Laplace transform? VCS is equal to 1 by C. Now, what is the Laplace transform of this IC? Integration of the Laplace transform. Integration of Laplace transform, integration of x dt. So, why do you integrate? And this is the Laplace transform for the integration. We have seen the differentiation here. Laplace transform of dxt dt. Can you remember? We have seen that in our previous lecture. S, we need to multiply S into xs. So we know the integration is opposite of the derivatives. Opposite of the derivative. So here this one will be 1 by s into xs. This is the Laplace transform of the integration. Any integration. So 1 by s, because the derivative will be multiplied and 1 by s. So here we have 1 by s into is. And there is a c, and there is a constant value c, and this c is equal to 0. Here we consider it 0 because there is no charge stored in the capacitor. In the beginning, there is no charge stored in the capacitor, so we assume that c equal to 0. So we don't keep that c. Otherwise, there is a c, cs into is. Now we can write it VCS equal to 1 by cs is. And this I is nothing but c. Capacitor current. So this is IR is for the resistor current, IC is for the capacitor current. So this is the modeling for this capacitor. Model mathematical equations. Next is the inductor. Inductor is easier because we already know that. The inductor L. So the voltage and current relation, it is V is equal to di dt. Rate of change of current in the inductor. That is the inductor voltage and current relation. So because we are using inductor voltage and inductor current, we use this L. And it is in time domain. So we will use this T. D-I-L-T. D. Now apply the Laplace transform. If you use the Laplace transform here, this VLT, it will be VLS. And DIL, T by dt. Here, the derivatives. This derivatives, we have an S term and XS. So S into I L into S. So here there is an inductor L. So the inductor with L will be multiplied. And capacitor, it is divided 1 by C. And inductance should be multiplied L by D. That is the equation for the inductor. So now we will see how we can add all these three equations in the same problem. The three different equations we have seen. All these three equations. So first of all, we have the VI relation. We have seen the VI relation here. VI equal to IR, VC equal to 1 by C, integration of IC dt, and VL equal to LDL. There is an inverse relation. Inverse relation, it is called IV relation. IV will be opposite because IR will be VR by R. Now here, if you want to find out this IC here from here, this is integration of IC. So if you want to find IC, so how do you find it? There is an integration term. So what do? We do the derivatives. So IC will be C into dBc by dt. Because if I want to find out, it is the inverse relation. So VL equal to LDL by dt. How if I want to find out IL? So IL will be equal to integration of VL dt. And here I have an and, so it will be 1 by n. So VI relation, VI voltage and current relation, and this IV relation are opposite. Remember one. Don't remember two, then you will be confused. Only remember this one. This VI relation, not the IV relation. VI relation. It is a common one. Remember this. Now there is an example, and this example there are two ports network. Two port network means there will be input and output. That's why they are called two ports. So this two port network, we have an input VI, and in the other port there is a Vout. We provide the input and there will be a Vout. So what we need to find out the transfer function. And what is the transfer function? What is the transfer function? Anyone? The relation between input and output. Input-output relation. That is the transfer function. So what is the input here? Input VI and output is Vout. So the transfer function is Vout by VI. That is your transfer function equation. Vout by VI. But in which domain? Laplace domain. So you must need to write it in S, not in D. We find out the transfer function in Laplace domain. We don't define it in time domain. So we are going. This is what we need to find out from this equation. So here we have R and C. No L. There is no L. So we will use two equations only for R and C. So how do you find it? How can you write it? So this one actually we use KVL. Do you know that KVL? Kirchhoff's voltage law. Kirchhoff's voltage law. Because when there is this VI, so it is a closed path. So in the closed path you can use this minus VI T is equal to, this is current flow I. IT. This is plus minus VI plus ITR plus 1 by C, because we already know that IC T dt is equal to 0. Now, you don't need to write it for IR and IC. You just write IT because we are defining there is a current IT. So this is your equation. So you just take this in another side. So you will get this VI equal to ITR plus 1 by CI. So this is called the KVL equation. Kirchhoff's voltage law. And apply here also. Apply this in here as well. In V out. There is a C and V out. So V out T is equal to 1 by C integration of IT dt. So now here you have VI, here you have V out. So you can use the equation and you can find out the value. So here, look at this. We are equal to 1 by C IT dt. So we need to find out V out by Vs. So what do? We put the value VIT and this and apply the Laplace transform. We already have seen the Laplace transform. So apply the Laplace transform and then rearrange the whole equation. You just write V here. You just take is common because here this value is converting into is and 1 by C integration of ITDD is converting into 1 by CS is. We have seen that integration term. So here I will write it down for the integration terms. So for the integration, we use the Laplace transform for the integration of x t dt is equal to 1 by s into xs. So here we have the integration term, it is 1 by s into is. Here we have the integration term 1 by s into is. So we just take common of is r plus cs. And here we have the cs v out equal to is. Now here this value is value, we just put it so this is value here we will put it CSV out, and now this equation what we can write VIS equal to CSV out into R plus 1 by CS. So we need to find out this V out. So what do? We will write it in this way. V out by VAS is equal to here. So it will be 1 over this whole CS into R plus 1 by CS. Now this two equation and this one we will write it R C S plus 1. Now this RCS plus 1, from here what we can find? We can find out the pole and zeros. Can you remember in our previous lecture we also did there? Pole and zero. Why? To find the stability of the system. to find whether this circuit is stable or not. So we can find this by using this is the poles, this is the zeros, and this are the poles. So how do you find out the poles? RCS plus 1 equal to 0. S equal to minus 1 by RC. S equal to minus 1 by RC. We don't have any S term here, so there is no zeros. So now how do you find the stability of the system? I already told you this is called LHP. RHP. Left half plane and right half plane. For a stable system, all the poles has to be in left half plane. All the poles has to be here. I already told you that in our previous lecture. For a stable system, all the poles has to be here. How many poles here? We have only one pole. This is minus 1 by RC. That means it is here. Minus. So I will have the value of minus 1 by RC here. Is it stable or unstable system? Stable system. Why? Because the pole, that is one pole, and that pole is in left half plane, left side. So it is a stable system. So the system is stable. System is stable. That is how you will find the stability of the system for any system. This is for the electrical system. We find out the stability of the system. So our system, our circuit is stable. If all the poles are in left half plane, if any poles in other plane or imaginary plane, right half plane, it is an unstable system. So here we find out. So it is. I have seen that this is the system has one pole and it is S equal to minus 1 by RC. So it is a stable system. Now design an electrical system that would place a pole at minus 4. Now the value is given of this pole. So the value is given. What is the value of the given? We already have found this pole, that is here. The value is S equal to minus 1 by RC, the pole that is. Now the value is given. This place a pole at minus 4. So this is the value of S. This is another example, not the same, another second example. So the value is given S. So here S is equal to minus 4, and we already know that from equation we have found that S equal to minus RC. So minus 1 by RC is equal to minus 4. So how you can make, what are the values? Now we need to find out the R and C value. R and C. What is this? R and C. The value of R and C. So how do you find it? There is you need to find out, you need to calculate R and C. So here, if R is 250 and C is 1 millifarad, so suppose 1 by 250 into 10 inverse 3, then it will give you a value of minus 3. So R value for this is 250 and C is 10 inverse 3, 1 millifarad. So R is 250 ohm, and 10 inverse. Just do this calculation: 250 into 10 inverse 3. So you will get the -4 value. So this is the pole. From this pole, if the pole is given, then you can find out the value of R and C. RC is unknown. If RC, R and C are unknown, if the pole is given, then find the pole, and from there you can find out the value of R and C individually from this by using this equation. Alright, now we will talk about the impedance. The impedance that I already told you. What are the impedance? Impedance is the opposite of the current flow. Impedance. Opposition of current flow in AC. Impedance only happens for the AC. So impedance happens for three different components: R, L, and C. So first one is the R, or the resistor. So suppose here there is an R. How do you convert this in AC? In AC we cannot directly write R. We have to write it Z. But we will write it as ZR because there is impedance happening for ZR only. In this circuit there is only R. Look, I will show you. Z equal to R plus JX. Now, if there is no L and C, X is for L and C. If there is no inductor and capacitor, then this value will be 0. So it is just R. And we can write this JXL minus JXC directly. So because Rx is equal to XL minus XC, X is equal to XL minus XC. Or plus XC, you can write it plus XC. So XL and XC are values of 0 because there is only R is involved in this circuit, no L and C. So we just write Z is equal to R. So for the resistance, the impedance is happening, so we write it ZR. Now for the inductor, we can write it L into S. In Laplace domain. For inductor, we can write it L into S because L is the derivative of the current. dIdt. So we have an S term. So we can directly write it for the ZL. We can write it L into S. Why we are converting? This is the conversion of time domain to the frequency domain by Laplace. We can directly write it. We also already have seen that by using different equations. So the L. So in the Laplace, the ZL, the impedance will be L into S. And what about the capacitance? It will be divided. It will be divided. Why it will be divided? Look, say here, go back. For the capacitor, after we do the transformation, Laplace transformation, we have found that 1 by Cs. So this one is for the capacitor. So the impedance will be 1 by Cs, 1 over Cs. So the impedance is happening for the capacitor in an AC circuit, we can write it 1 by Cs because it is for the capacitor, so we just write it Cc 1 by Cs. So for the inductor it is L into S, for capacitor it is 1 by Cs. These are the impedance for in the Laplace domain, impedance in the Laplace domain for the electrical circuit in for AC. Now here there are two different types of combinations, equivalent circuit for series and parallel. So for the series, mostly this is the series combination RLC. It is in series. So why these are connected in series? We actually write it R equivalent is equal to R1 plus R2 plus R3. In series we write this series connection. These are in series connection. RLC are in series connection. So we can write it because it is in AC circuit. We define it in Z. In the DC circuit we define it in R. But here in the AC circuit we define it in Z. Z equal to ZR plus ZL plus ZC. So for the ZR we have the impedance, and for the ZL we have NS. For the C 1 by CS. This is just an equation, series equation, resistance, series, equivalent resistance for the series. Again, equivalent resistance for the parallel circuit. It is 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. This is what we know. So again here this RLC are in parallel. This is in parallel connection. So in the parallel connection we will write the same format in the AC circuit. 1 by Z, T means total. 1 by ZR, 1 by ZL, 1 by ZC. So we just write it because we already know ZR, ZL, and ZC. So here we have the values. So these are the two different combination of series parallel equation. And these are all about the mathematical modeling. In the next class, we will talk about the transfer functions and block diagrams. Very interesting for you.